Just welcome you all here, those of you here in person and those on Zoom. We have a special presentation tonight. We're going to be talking about the Noetic flood in Genesis, and probably that's one of the best known Bible stories, both for believers and non-believers. And certainly we all grew up with the caricature of the animals getting on the ark with giraffes and elephants and snakes. And oftentimes the snakes had a big smile on their face, at least in the books that I've seen. And I'm not sure I've ever seen a snake like that. But anyway, it gave a picture of a global flood of animals all over the world. But the question is that what really Scripture says? And is that what the science permits? And so we have a special guest tonight. Patrick McGuire is coming to speak with us. Patrick is a petroleum engineer with 44 years of experience. He is a noted expert in enhanced oil recovery and has worked on complex enhanced oil recovery opportunities across the globe. He authored numerous technical papers on the subject and holds 7 U.S. patents. Patrick also served as a Society of Petroleum Engineers Distinguished Lecturer and has addressed over 30 Society of Professional Engineers sections around the world. He first became acquainted with reasons to believe in 1987 when he met Hugh Ross in Anchorage, Alaska, where he was living. He then became the president of the RTB Alaska Chapter before moving to Denmark in 2009, and has spoken on intelligent design to science and engineering students in China, amongst other areas of the world. Patrick is currently working on oil field projects in Alaska, Azerbaijan, Oman, and the continental United States. So Patrick, we are delighted to have you here. Let me say a word of prayer, and then we'll turn it over to you. Father, we are grateful to be able to be here tonight. Thank you for getting us through the technical challenges, and we just pray that you would allow your truth and your word to enlighten our minds and help us, Father, to understand you better, help us to know you better, and to be better ambassadors for you in this world. We thank you in Christ's name. Amen.
Yeah.
Patrick, thank you very much.
Okay, and I had a Zoom meeting with the folks in Azerbaijan this morning, and everything was working fine. And I found out I had to upgrade my Zoom because you guys couldn't tolerate anything as ancient as what I had. So I'm going to try to figure out how to share my screen because you don't need to see my face. Let me see if I can find out how to share in this new share screen. Let me share screen. And I'm going to start this slideshow and hopefully share the slideshow. So give me just a second. Uh-oh. Now I can't see my Zoom screen. All right, what are you guys seeing now?
Oh, got it. Okay, good. So we see recommended 0.5, that thing, right?
Oh, that's the wrong screen. That's my project in Texas. We probably better not show that one. This is All right, let's see if I can. What do you see now?
Yep. Why am I doing geology?
Ah, okay. Is that full screen or
No, it's not full screen.
It's close enough.
close enough? All right, what I can do, close enough. I like your attitudes there. I'm going to make it as big as I can.
Close enough for government.
No, it's way too close to that.
All right, I think that's as good as I can do.
That's good.
Okay, so I was asked a long time ago, and please let me know if everything is visible. But I was asked a long time ago by Reasons to Believe, since I had I'm not a geologist, but I have a pretty good geological background. And I was asked by a gal named Krista Bontrager, if you remember her, to answer a couple of questions for Reasons to Believe. So that's what we are going to endeavor to do this morning. Okay, this is going to force me to click buttons, but I can live. Okay, so why am I doing geology talks for Reasons to Believe? Well, I've got at this point in time, a 45-plus-year career in the business as opposed to the science of geology and biodeposits. And those were the subjects I was asked to address. So I'm actually competent to answer the questions for Reasons to Believe, and hopefully you'll agree with me once I go through an example. There was a great quote by a well-known individual named Galileo Galilei. And he was a pretty good theologian as well as probably the first scientist. And what Galileo said was, the heart cannot rejoice in what the mind cannot accept. And that has been a pretty important quote for me, because I've had my struggles in this area. And then there's another quote by somebody not as well known as Galileo. And there was this Sunday school teacher that posed a question for his Sunday school class. And he asked the class to define faith. And I believe the kid was 10 years old. And what this boy said was, faith is believing what you know isn't true. And I mean, usually people laugh when they hear that. And it's funny, except when you're living it, it really stinks. And basically, that is where I was for 12 years between 1982, let's see, 75 is when I graduated and got out of school and started in the oil industry. So between 1975 and 1987, I had a 12-year struggle trying to reconcile young Earth, young Earth creation geological stories with what I was learning in the field. And my degree was in mechanical engineering, and I trained for the nuclear industry. And I was all set to go to work for General Electric in San Jose doing thermal analysis of reactor cores, when all of a sudden that didn't happen. And I ended up working for a company called ARCO, which, because you guys are good Californians, you probably remember ARCO. So I became a petroleum engineer, not by degree, but by working in it. And I had a 12-year struggle with what I was learning on the job versus what I was being taught in Sunday school class. And it really bothered me, because I place a very high value on truth. And I think most of us do. So again, I met Hugh Ross in, I think it was springtime of 1987, but I won't swear that it's spring. But he was presenting several days worth of the early RTB material. And I think RTB started in 1986. So this was really early on. And Hugh was up in Alaska doing 3 days of talks at First Presbyterian Church, which was 2 blocks from the ARCO building where I was working. So I was interested in this subject. So I went and I listened to this Southerner. He's a Southerner to me. I'm an Alaskan. Uh, so I listened to Hugh, and he looked like a scientist even back then. He was pretty bald and just looked like you should expect a scientist to look like. And I was very impressed with this man. And I was really good at science. I never met a science or engineering course except for one that I didn't like. And so I was able to evaluate, scientifically what he was saying. And yeah, this guy's, he's right. He's credible. But what blew me away was I listened to the theology of the old Earth creationism, and I'd never heard it. It was kind of young Earth creationism, my way or the highway, and that was sort of how I lived those 12 years between 75 and 87, and that's not what I wanted to do. So I listened to Hugh. I got every piece of literature that the Reasons to Believe ministry had, and I studied it diligently. And one of the things that had occurred to me, and I think Hugh might have even said this, was when you're talking about God, God is the author of truth. I am the way, the truth, and the life. That's what Jesus said in John 14. And God's truth in nature and God's truth in the Bible, which is his word, if God is the author of both of these, they have to mesh perfectly. There's no room for error if the author is God. So they're going to mesh perfectly. Now, science is man's interpretation of God's truth in nature. Theology is man's interpretation of God's truth in the word. And these interpretations, they can miss completely. They can be a little overlap. There can be a pretty decent overlap. But if our interpretations are correct, they too are going to mesh completely. God's truth in man's science are going to agree with God's truth in man's theology. We have a problem, though. Unlike God, we're not perfect. We're very finite. And so when these things don't mesh completely, we have to have humility. And humility is a very good thing for us always to have. It says, for example, Peter says, be ready always for a defense with the hope that is within you, yet with gentleness and reverence. So we have to have the humility to realize one interpretation or the other interpretation, or maybe even both of our interpretations, could be in error, either partially or quite a bit more than partially. And so we have to have the humility to realize that when they're not meshing, we have a problem. It's not God. We have a problem. And we need to have the humility to address our interpretations. And so this concept, I think, is really important. God's truth meshes with God's truth. And whatever we do, both theology, science, God's truth in nature, God's truth in the word, they should mesh completely. And, after listening to Hugh for these 3 days, I studied all the materials RTB had, and I was really impressed. I became the Alaska Chapter president. There wasn't a chapter in Anchorage at the time. So we started one, and I was the president until we moved to Denmark in 2009. And the fourth point here on my slide is after this reconciliation, where I now had confidence. Before I struggled, now I don't. I have confidence that God's truth meshes with God's truth. And that's drastically improved my confidence in sharing with scientific audiences like engineers and the geoscientists I work with. And the Lord opened up opportunities later, starting around the year 2000, for me to give evangelistic outreaches in mainland China. And I was able to share with a group the church was having trouble reaching, and that was engineering and science graduate students. And I got to address these people at some of the very best universities in China. And I mean, my faith was rock solid, and I studied good science. So I shared with the best, smarter people than me by far, with great confidence, because I knew I had truth meshing with truth. So anyhow, RTB had a major impact on my life, and I've been involved with him for a long time. Okay, this slide that I'm showing you now, this is the difference between a scientist, a geologist, and an engineer. And the science guys, I mean, I love science. The science guys can be a little bit detached, but the company employs the engineer to do projects and to make them money. And it's a very different focus. And so I don't know if you can see my pointer or not. Can you guys see that?
Yes.
Okay, that's great. I'm going to see if I can do something intelligent right now so I don't have to do this again. I've got pointer options. Well, I won't worry about it. Okay, so the way a geologist looks at things is this is, for example, what a well would look like if you drilled a well through several hundred feet of rock and you took a core sample, which is typically about 4 inches in diameter. And I've processed a lot of core, especially up in the Arctic. And what the geologist looks at is he looks at sands and shales. But he always starts at the bottom, kind of figures out what's going on. And he would look at, for example, this Delta Bar deposit, and you would see these yellow. This is actually a gamma ray log, and these yellow deposits are sandstones. And so, what's called a distal deposit in the lower shore face. You'll hear a lot of geologic words, and I'll try to describe some if there's questions. But as you go up in the section, you get closer and closer and closer to the beach. And as you start getting closer, you start to get more and more sand, and these sands get thicker and thicker. And finally, when you're at where I've got the word sand, where my pointer is, you're on the beach. This is however thick the beach deposit may be. And then as you keep going up, you start to get overruns. If the water overruns the beach, you deposit some mud, get another transgressive event, a thinner sand comes back, and then a thinner one. And finally, at the very end here, you're completely buried by shale. This is way offshore. There's no more sand. But you're looking at a time sequence that may cover hundreds of thousands to millions of years in this couple hundred feet, possibly, of core. And the same thing can be said for fluvial deposits. Fluvial is the fancy geologic word for flowing water. And then a turbidite deposit offshore, it's essentially a submarine landslide. And so you get this big deposit that's going down the continental slope, and it's rolling along, and the heavy stuff like the rocks, that gets deposited first, and then gradually the heavier stuff, and then the lighter stuff, and then the even lighter stuff, and then the very lightest stuff settles out, and it forms what's called a turbidite deposit. This fancy word for submarine landslide, but these things look very different to a geologist. This is what he does to try to understand the real world. And the first thing he does is he tries to figure out what is the depositional environment I'm in. And then he's ultimately looking for something like this, where you've got muds or siltstones, various fine-grained sediments that have a whole lot of dead critters in them. And these critters are usually phytoplankton. They're not dinosaurs. They're not even fish. They're little bitty critters. And sometimes you can have as much as 10% of this rock be corpses of these little microscopic phytoplankton. And this is what cooks over a lot of time and high pressure and high temperature. It cooks gradually in God's crock pot. That's what I call it. That makes oil out of these little dead phytoplankton. And then this oil migrates out of this rock, and it gets into sandstone, and then it forms, the oil goes up, it floats up because it's lighter than water. And then quite often you'll have gas in there, natural gas as well, and that's even lighter than the oil. And so you form something like this. You've got water on the bottom, oil in the middle, and maybe not, you've got gas on top, and it's all trapped underneath some sort of a fossilized clay, which is essentially a shale. So some kind of impermeable deposit. And presto bingo, you've got a petroleum system. And this is great. The geologist has done his job. Now I have to do mine. And my job is I don't live in a world of rocks. And what you see here, these brown things, this is a thin section. And these brown things are actually sand grains. And the fluids are trapped inside the pore spaces. So there's little holes in the rock. They're called pore spaces. And that's where my world comes in. You know, Arco didn't pay me to try to make rock. There's plenty of sand in the world. They wanted, my job was to get the oil out of this petroleum system and send it to California so you guys could make gasoline. And so what I look at is what kind of processes do we employ to drive this oil out of this oil field, this petroleum system, and into your gas tank. So, and I can't possibly do my job unless I understand quite well the geology that we're looking at and what those pores look like. So our thought processes and our disciplines are very different, but the geologist and the reservoir engineer, we're joined at the hip. We really need each other to get you guys gasoline. And so this is what I've been doing and still am doing. And now I'm going to describe for you Field X. And I don't want to tell you what Field X is. The name of it, I'll just say it's in the panhandle of Texas, and it comes from Colorado. It actually comes from Colorado Springs, which is where I live now. So in the upper Pennsylvanian, which is just a little over 300 million years ago, this is what the world looked like. Kind of you spread it out on this map display so you can see all the continents. And there's a continent down here. I'll find out, or I'll tell you later about Gondwana. But a bunch of the continents, actually even more of them than in this picture, were all around the South Pole early on. And that actually caused glaciation. And glaciation is very important for Field X. Okay, so let's take a look at Field X. This is the Texas Panhandle. These are the ancestral Rockies. This is the ancestral Front Range, and this is 350 to maybe 280 million years ago, long time ago. And this square here, that's a formation called the Garden of the Gods. It's a park in Colorado Springs. It's a pretty amazing place. And the old seafront, this thing called a high stand, this is as far up to the north as the sea levels got when this is deposited. So southeast Colorado was underwater, and the shoreline was very close to Colorado Springs. And then the glaciers happened. You got all of this in here, southeast Colorado, Oklahoma, Texas. This was all seabed. And then because of the glaciation, the seawater levels dropped. And so you're now down here in what I'm calling jokingly the Oklahoma Ocean. It's that really was where the beach was, just 306 million years ago. This is called a low stand, and that's as low as the beach deposits actually got. And you had these rivers that were running from the ancestral Front Range across Colorado and Oklahoma and into Texas. But the beach was essentially the Oklahoma state boundary. And this is a formation called the Upper Morrow. There's a whole string of oil fields that are along this ancestral river system. So what we need to do, as I've already given some of the story away, but we need to take a look now at planet Earth as a whole to really understand the depositional system that my oil field X was in. And what I've got plotted here is on the y-axis, this is the carbon dioxide level in the atmosphere, which is currently 420 parts per million. Well, back in this Ordovician time frame, that was like 460 million years ago, 450 million years ago, excuse me, the first mass extinction on planet Earth took place. And it killed, it's 80 something percent of the species in the oceans. There wasn't really much on land at that point in time, but like 80% of the species in the oceans, they went extinct, they died. And that qualifies it as a mass extinction is greater than 75%. It's the second worst mass extinction in history. The worst was the Permo-Triassic, which is called often the Great Dying. And that was the most massive extinction. I think like 90 something percent of the species, just at least in the oceans, vanished. But this first mass extinction, I showed you earlier how all the continents were kind of down in the south in this Gondwana. I think later when it became a single continent, it was called Gondwana land, but it was just Gondwana back then. And so you've got carbon dioxide levels that are very high. The temperatures here, this is shown in blue, and this is on this other axis, the second y-axis, and it was pretty warm. And then all of a sudden, CO2 levels are very high, but basically the Earth froze. So what happened? Well, it appears that this mass extinction was caused by a gamma ray burst. So here is where the universe is playing games with planet Earth. And so you get this giant gamma ray burst, and it destroys Earth's ozone layer. And so anything on land is just destroyed with ultraviolet radiation. Anything in the shallow oceans pretty much is also destroyed. And you lose a lot of the greenhouse effect with this ozone layer gone. And all of a sudden you've got freezing, and you start to get a lot of snow at the South Pole. And now you've got a feedback loop and a feedback loop and a feedback loop. It just gets worse and worse as the glaciers grow from the south. And so the temperatures fell, but CO2 didn't. And so with the ultraviolet and the freezing, again, that took out about 80% of the species in the shallow oceans. So the first mass extinction event and the first appearance that I'm aware of glacial, growing, shrinking, growing, shrinking, huge effect on the geology and the depositions in planet Earth. And then CO2 continued its long gradual trend down to where we are today at about 420 ppm. Things rocked along, temperatures were pretty nice. Plants appeared on the Earth, but these were weeds. So there's only so much biomass that you can put into weeds. Then in the late Devonian, just before the Carboniferous period started, trees appeared on land. And so these things were big. I mean, we're talking 100-foot trees. These aren't weeds, these are trees. So you've got these huge coastal forests, these flat-lying swamps, and these trees would grow and die, fall into water, grow and die, grow and die. And there wasn't anything that could process the lignin from the cellulose in trees. So fungus couldn't eat it. It would not rot. It became coal. And the last half of this Carboniferous period is the Pennsylvanian era, and that's where all the Pennsylvania coals got laid down. And then our friend Mr. Evolution or Mr. Creation, I don't know which, but all of a sudden this stuff called white rot fungi appeared. And now you finally had an enzyme that the fungus could use to decay lignins and cellulose. And all of a sudden you got this massive rotting of all these dead trees. And so your CO2 levels that were in the black here, they went down and then they spiked back up. And this, along with the great eruptions in Siberia, led to the biggest mass extinction event in history. And that was the great dying at the Permo-Triassic. And the temperatures had gotten very cold. They have not been as cold in the last 300 million years as well, they were that cold 300 million years ago as they are now. We're in an ice age. The last 2.5 million years, we've had glaciers, in a lot of places like my home state of Alaska, and we had them back then too. And these glaciers, they would advance, they would recede, they'd advance and recede. So this sets the global environment from which the geology of Field X can now be examined. And so here's a kind of a cartoon diagram of what Field X looked like. And basically, let's just say this is Colorado Springs up here, and this is Oklahoma down here. And, you've got basically mud. You've got mud being deposited from central Colorado all the way into, what was then the Gulf Coast. And so there's a giant mud bank that is laid down in very deep water. And then you have the glaciers come, and the glaciers basically dropped sea level. As glaciers formed on land, excuse me, the sea levels dropped. And now you had these ancestral river systems flowing across this muddy bottom. And it's going all the way to Oklahoma and Texas. But what used to be beach in Colorado, this is now dry land. This is, you got glaciers up here, glaciers and snow. And it's running through what's called an incised valley, as all this high energy river system is flowing across this former seabed, which is mud. And so you've got all the Colorado sediments running downhill at a pretty good velocity, being mixed with some of the sediments from Texas and Oklahoma. So this is how a sedimentologist, a specialist in these kind of depositional systems, a geologist, would describe this. I took this right out of this paper on unconformity controls back in '94. Sandstone reservoirs in the upper Moro of eastern Colorado and western Kansas are the deposits of incisive valleys which were cut during glacially induced sea level drops. So basically, the sea level drops, the beach goes down toward Oklahoma, and you've got the river doing its miniature version of the Grand Canyon through this old seabed. And then gradually filled with sediment as base level rose during the interglacial transgressions. So this is a transgression. So you lay this thing down, and then you get the glaciers melt, the sea levels go back up, and you get this entire valley now covered with mud again. So it's got mud below, it'll have mud above. And they've got some sizes of how deep and how wide these things are, 50 to 80 feet deep. Well, Field X is about 50 feet of sandstone sediments, and 0.5 to 2 miles wide. Field X is about a mile. And I'll show you what it looks like in more detail later. So this is the system, again, with some little more geological accuracy here. But basically, you've got the river system flowing, from my house in Colorado Springs down here to the Panhandle just south of the Oklahoma border. And then here's the Oklahoma Ocean is this blue stuff here. So that's where the sediments came from. It's how it was laid down. Now I'm going to change gears very quickly. You're going to ask, why the heck is Pat showing a picture of the Russian Arctic? I'm grabbing onto a Russian wellhead here a few years back. I'll never do this again because I can't work in Russia anymore. But when I was flying to the Russian Arctic, I started from the town of Tiumen, flew to Novi Urengoy, which is the Gasneft, the company town for the Russian natural gas company. And then 2.5 hour helicopter ride north on a Russian military helicopter. I'm up here in this Russian oil field in the Arctic, which is kind of familiar because I spent a lot of time in the Alaskan Arctic, and it's all crummy. The reason I'm showing this picture is I'm on my flight to Novi Urengoy, and I'm going over this river system. And I said, this is the best example I have ever seen of prograding point bar deposits on a big river system, or a medium-sized river system. It's not the Mississippi, but it ain't no creek. And so what you see is these are what are called prograding point bars, and the deposits will gradually work their way outward and outward, and the bend will get tighter and tighter, and then eventually it'll cut through. And quite often, and this is called an oxbow. This is an abandoned channel. That's exactly what Field X is. So the way it works from a geology point of view is the river system, you're eroding this outer bank and you're depositing sands because the velocity is high here on the edge. It's turning, and this is where the erosion is taking place. The sediments are actually getting deposited on what's called a prograding point bar. And like this one, eventually it could do what's called a cut bank right across, and then this would become an abandoned channel. And this is the best I've ever seen, looking at this, I look for this kind of stuff when I see geological formations. This is just the cleanest example I've ever seen of it. And this is the Ob River, flows northward into the Arctic. And then this, I spent a lot of time in the town of Tiumen, which is, I think maybe it's 30 miles or so from this village of Leshnoya. That's the Cyrillic for Leshnoya. If you know the Cyrillic alphabet, there's the English, and that's what the Russian looks like. And the flow is this way. And the prograding point bar, it started here and it grew and it grew and it grew and it grew and it grew. And it hasn't cut through yet, but sooner or later, left on its own, it probably would. But this is good farmland. All this stuff in here is cropland, and it's being farmed. It's got good, it's good stuff for a farmer. This out here, this is all sand. It's not really something you want to plow or plant something on because there's no nutrients. It's just sand. But this is almost exactly like here's Field X. And so we've got this prograding point bar going out through here, flowing Colorado to Texas, north to south. And then we've got a feature here that's called a splay, where it gets a lot thinner. And this is what a splay looks like. Again, here's my prograding point bar. And then during some big flood event, you'll rupture the levee wall, and you'll get all this sediment flow outside of the main channel. So there's a lot of good sandstone deposited in here. And then you have this rupture, and you get thinner volumes of sand that are in this case, being prograding eastward, and then it's done. And that's what Field X has. It's got the main channel, and it's got this crevasse splay deposit. So you can see this. I'm not doing any of this to do Noah's Ark. I'm trying to figure out what's going on in this field so we can develop it. Okay, here's my cursor. So we're going to go back to Colorado, and we're going to see where these sediments came from that formed Field X in Texas. And there's two formations here that I'd like to show. One of them is called the Lyon sandstone, Lyon, and the sediments were laid down kind of like this. The Pikes Peak Massif came up to the west, and that's where 14,000 something feet 14,130, whatever it is. It's one of the 14ers in Colorado. And it turned these sediments, this uplift of the Pikes Peak Massive turned these sediments where they're pointing to outer space. They were laid down flat, they were tilted. And so that's what you're looking at here is these tilted fossilized sandstone formations. These are deep desert deposits. It's basically sand dunes, fossilized sand dunes. And if you look close, you're probably going to have a hard time seeing it. But where my pointer is, there's rock climbers here. This one guy up top is belaying his buddy to the top of the formation. There's another rock climber here. And so these are big fossilized deserts. I got some, if I can get my cursor. These are really cool deposits. I mean, there's a million people a year visit this Colorado Springs. Really cool. I'm a nerd, so I look at the geology. But this is these are frosted sand grains. They're windblown. They're not river stuff. This is desert. And windblown desert deposits, they get scraped by other sand grains and they get what's called frosted. It's kind of like you've got a layer of smeared white on the red sand grains. And that this is a close-up of it. This sign is about 5 meters, about 15 feet across. So this is big stuff. Now that's all sand dunes. This is deep desert deposits, and I use the word deep desert because go right into the heart of the Sahara Desert. That's what this continent looked like when these sandstones were deposited about 300 million years ago. Actually, this would have been about 260. Now here's another formation. It's older geologically, and it's this is just composed of meandering rivers. This is what the geologists would call fluvial. And it's the Fountain Formation. It's a little bit south of these big sand dunes. And what you can see is different layers, and a good geologist will always start at the bottom. So here, this is coarse-grained pebbly sandstone. If you look, you can see some pebbles in here. It's mostly coarse-grained sand. For scale, this is the hand grip, left hand grip of my mountain bike. No, right hand grip, doesn't matter. Anyhow, this is the hand grip of the mountain bike. That'll give you some idea of the scale of these things. So you can see boundaries, bed boundaries. This pebbly sandstone goes then into well-sorted medium sandstone. This is poorly sorted, big. This is medium grained, and it's well-sorted, back into coarse-grained, back into medium grains. Each one of these is a big flood event, not a NOAA's flood, but a like big, massive spring melt. And the glaciers all melt, and you get the outwash, and you get different beds. This one here, this conglomeratic sandstone, you're starting to transport some pretty big stuff here. This is not sand. This has got rocks in it. So this is typically what you see like in a fluvial formation with rivers. Looks nothing at all like the sand dunes in the Lion Formation. And then this is a good modern analog, we think, of the river system in the ancestral Colorado Springs. Again, the paleo climate was not that different than ours. The temperatures were, Colorado was cold back then. It was, it got hot before and it got hot later, but it was cold back when this was happening. And this is what we think the Garden of the Gods might have looked like way back when. You've got mountains with glaciers and snow, and then this stuff melts, and this is an outwash plain, and this is a high energy system. It transports a lot of big stuff. And this is the way that a river or a stream transports washed away material. Detritus, I think, is the right geologic term. And so you've got here's the previous bed, and now you've got this flood event coming along, and it's rolling rocks and sliding rocks and rolling and sliding, and the big stuff stays right on the bottom. And the sand, it's dissolved, not dissolved. It's being carried by the water. The rocks are rolling along the bottom. The sand is in the water, and as soon as it slows down, the sand falls out. And then you've got silts and clays up here, and that stuff stays suspended. So this is the textbook, and this is how it's supposed to happen. You have heavy stuff on the bottom, it's mixed, it's not well sorted up above it, it's well sorted, and then you got, none of this probably ever gets deposited or rarely does. Now that's the textbooks, and I took at my turnaround spot where you saw my handlebar on my mountain bike. Boy, that's exactly what we see. Here's this old, the old boundary, and this white layer, that's a layer of cementation. That means this rock was on the surface and it was exposed to evaporation and various things, probably for years. But it formed a kind of a cemented hard surface that then the next flood could roll these rocks across, and you basically, the heavy stuff's right on the bottom, just exactly like the textbooks show. And then you gradually get into more of a sandstone, but this is a definite conglomerate down here. So the geologic description of this: conglomerate and pebbly sandstones containing thin layers of dark reddish brown shales. That's this silty crap in here that sort of got mixed in with the big rocks. Reddish brown shales deposited in a high energy outwash plains from eroding red granite, which this Pikes Peak granite, it's the same granite back then, 300 million years ago, that we got showing the surface today. Anyhow, that's how the sediments got laid down in Garden of the Gods. Now you can imagine this stuff never going to make it to Texas, the rocks. But this stuff up here just might. So let's take a closer look. And excuse me, for scale, this is the tire on my mountain bike. It's, I think, a 29-inch tire. Not that that's important, but that gives you a scale. So this is going to be 2.5 inches or so. And these rocks here, the ones I've got the yellow arrows on, they are part of the formation. They're locked in, they're cemented in. This is all one depositional system. But these guys, these yellow guys, they're never going to make it to Texas. What will make it to Texas is this stuff in here. It's still pretty coarse grained, but this stuff can actually be washed by the river system downstream. If I can find my cursor again, there it is. Okay, so now we're going to leave Colorado and we're going to go to the panhandle of Texas. And I've got a penny here for scale, but what you can see is this is what's called granule conglomeratic sandstone. And basically it's stuff that's a little bit bigger than coarse sand, but it's not rocks. It's basically just coarser than what we typically classify as sand. And that's sourced in Colorado. Now remember, we're flowing across an old seabed. And so you get these things, these are called rip-up clasts. It's a mudstone. It's the muck that was on the bottom of the ocean when it was laid down. And it's pretty weak, but it still will hold together. And this stuff gets washed off when the river's really high. And so you deposit this mud from Texas and this sandstone from Colorado, and it's all down here in Texas. And that's the field X that I'm trying to deal with. And we put all this information together, and I'll work with a geologist, a petrophysicist. He's the guy that studies the rocks, and he's an expert on rocks themselves. And then a geophysicist who sends the sound waves down from the surface, and we map out the structure. And then so you've got these 4 guys: geologist, a petrophysicist, a geophysicist, and a reservoir engineer. And together we build a mathematical model of field X. And so that's what it is. And these lines that you see here, these are The red ones are injection wells and the black ones are production wells. And this has been drilled up, and we know how thick the structure is, what the tops are. So we can make a mathematical three-dimensional model of field X, and that's what I'm showing you here. So a long introduction to how I'm going to use a very tacky word, real geology works. It's complex. It fits into the entire global system of climate, the continents, the oceans, and then it gets more and more local as you look at sediments that are being deposited in these flood events of different scales. So with that background, I hope you guys trust me that I think I'm competent to ask the questions that our RTB wanted me to answer. And they posed 4 questions for me, 2 of which had to do with fossils and speciation. And I'm hopelessly not an expert in fossils and speciation. But the 2 questions that I did decide to answer: could the entire geological record have been laid down quickly thousands of years ago in a global flood? And question number 1, that's the sediments. Question number 2, could all the biodeposits have been formed thousands of years ago in a global flood? So biodeposits, for example, are like the phytoplankton, you know, the dead critters that settled out in the marine muck at the bottom and got cooked into oil and gas. That's an example of a biodeposit, is these dead bodies. Another biodeposit might be limestone, you know, coral reefs and stuff like that. So you've got sediments and you've got biodeposits. And now you're going to start to see my answer for this. Before I give you my answer, I think it's only fair to let you know what I believe about Noah's flood. And it's pretty well, I think, the RTB position. I don't say it was God's judgment on mankind. I prefer to think of it as God's redemption. Mankind had gotten so corrupt that God figured out, if I'm going to save this race of human beings, I've got to basically do some serious house cleaning here. So I've got to save humanity. It's redemption. It was real. There's flood stories in almost every culture. If you get ancient enough, you'll find a flood story in there somewhere. And humanity was redeemed through the 8 people on the ark. That's Noah, Shem, Ham, and Japheth, and their 4 wives. That makes 8 people. And then if you look close enough, a lot of the sin that humanity contaminated itself with also went into their animals. And so those animals that were contaminated by man's sin were also taken out at the same time. No need to kill the penguins in Antarctica. They weren't contaminated by human sin. And I'm not a theologian. I don't know exactly what's involved in sin in animal life. I do know what it looks like in human life. So it's a plan of redemption. This is the great flood, Noah's flood. And when you go through the book of Genesis and add everything up, you'll see that it's just over a 1-year period. They enter the ark. I think that was the 7th day, rains. 40 days, 40 nights, it just rains like crazy. I guess after they entered the ark, 7 days later, it rained. And then it sat there and basically floated. And then the flood peaks, we got the dates for this. And then you hear the mountaintops show, the ark comes to rest, and you can see mountains off in the distance, but there's nothing but water around where the ark's at. And then Noah sends out the ravens and the doves. The earth dries up. They leave the ark. The whole period of the flood, as described in Genesis, is just over a year. So what I also believe about Noah's flood, it was universal, but not global. And by that means humanity, or at least all the humanity affected by the sin of the human race. That was what was destroyed. But every place name that you can figure out until Genesis 11, every one of those is occurring in Mesopotamia. So this is where humanity, as recorded in the Bible, lived, was Mesopotamia. And what I also believe is the flood left very little impact on the geologic record, and you'll see why that is later. And it played no role in forming the biodeposits that we now utilize. So there have been a lot of really excellent papers and work done on the geology of the earth and the geology of Noah's flood. I'm taking a different tactic on it. I'm not going to be talking about the rates of deposition of sediments or the tree rings or coral, how much coral will grow per day, per year. Not going to talk about varves, which are these very fine-grained sediments at the bottom of lakes and stuff. There's been a lot of work done. I'm not going to talk about nuclear decay rates, and I firmly believe in all that stuff. It's good physics, it's real. But I'm not going to talk about that. What I'm going to talk about is something I think you've already seen from what I presented, and that is complexity. And let's take, for example, Field X. The Field X, the geologic record that I went through, it's very complex. I mean, we had to understand all this stuff, including the glaciers in the overall planet Earth in the Carboniferous period, to explain why these sediments from Colorado, high energy sediments or high energy river system, washed fairly coarse sediments, but not rocks, down to Texas. They got deposited in this old seabed. And it's a pretty complex history of the real geology, and I'm going to get into more of that. But the Genesis flood itself is a very simple event. So it's got what's called a transgression. You got one transgression where the water goes up, up, and up, and then it stops. And then you've got one regressive event, which is where the water recedes, and it just recedes. And we're going to go through the Bible on that right now. But for all its importance, the Genesis flood is a very simple geologic event. So if you look at it, the verses here, I've just got them. I think I'm using the New American Standard for all of this, but it doesn't matter. Pick your version. Chapter 7, verse 17, water increased. Verse 18, water prevailed and increased greatly. 19, water prevailed more and more. And then verse 20, water prevailed 15 cubits higher. So you've got one transgressive event. That's when the ocean is overrunning the land, and it just comes and comes and comes and comes until it stops. There's no going back and forth and back and forth. It's just one increasing monotonic event. Monotonic means it's got one direction. And then let's take a look at the next set of verses. And we're now in Genesis 8. And it's one monotonic decrease in seawater level. Verse 1, water subsided. Verse 3, waters receded steadily. Verse 5, water decreased steadily. So there's no up and down here. Once it started drying up, it may have slowed down, but it's monotonically decreasing. It's drying up. And by verse 13, water was dried. Total duration, roughly 1 year. So from a geologic event, geologic thinking, it's one transgression, one regression. It's a very simple event. And what I'm going to show you, I've given you some clues already with Field X, but the geologic record is very complex. There's many depositional processes, many structural processes, and we'll go through all these. There's chemical and thermal processes going on as well. So I'm going to give you two examples of geologic complexity. And one is in southeastern Utah. And we went, it's the world's best geologic training site. I don't think there's a lot of dispute about that. We went down there quite often from Alaska to study the rocks that we were producing oil from, underneath 9,000 feet of ground and 2,000 feet of permafrost in Alaska. Well, you're never going to see that rock. You're never going to put your hands on it other than one of these like 4-inch diameter core samples. But you can see the exact same geologic depositional systems, facies, facies associations, lithofacies, structural elements. You can see all this stuff in 3-dimensional relief in southeast Utah because it's a desert and because all this geology, this sedimentary geology is laid out for you to see. And basically what you need is a rock hammer and a truck, and you can drive and see all kinds of cool stuff. And then, I spent 30 years in Alaska, and I worked up here in the Arctic. It's why the Russians liked me. They knew I understood the Arctic. And it is the biggest and best hydrocarbon province in North America. The number 1 and the number 2 oil fields in the United States of America. It's the Prudhoe Bay field and the Kuparuk field. And now, with all due respect to my Canadian friends, people in Alberta may disagree. That's a heck of a good petroleum province down there as well. So I'll cut my Canadian friends some slack. They could dispute my biggest and best, but I'm an Alaskan. That's what I think. So here's what's called a generalized geologic map of Utah. And this is the area around Arches National Park that we're going to look in detail on. And this is the stratigraphic column. And that's the column of if you were to drill and take a core sample all the way from the surface to the basement rocks, the Precambrian, this is what you would see. And I know it's going to be difficult for you guys to read, but I've sent the PDFs to Randy and Jim, and you should be able to get a copy of this. But what I want you to look at is this thing titled geologic events. And let's go all the way down into the this lowermost section, Pinkerton Trail, doesn't matter. We have marine limestone, a transgressing sea. So that means limestone, and with the seawater getting deeper and deeper. And then cyclic deposits, the next, the Paradox Formation. There's also a bunch of salt deposited in this. It's an inland, landlocked lagoons. So this is where the ocean has been trapped by ground on all sides, and now it's a lagoon, and it's getting evaporated, and you're going to leave all these evaporite deposits, these salts. And then the Honaker Trail, and you're going to see some of this. We'll show you some pictures of the Honaker Trail. Cyclic deposition, limestone, sandstone, shale, salt in a shallow sea. Up one more, alluvial fan, and that's the stuff, you got a mountain, and the outwash plain, just when the mountain hits the plains, it leaves this, what's called an alluvial fan. Go up into the the Chinle, braided stream deposits. Next one, lake and river deposits, stream and lake deposits. And then we're starting to get into some of the fun stuff. The Wingate sandstone dune deposits. Oh, excuse me. These are like the giant sand dunes that I showed you in the Garden of the Gods. These are Sahara Desert fossilized dunes. And you don't have to be a rocket scientist to look at these things. And yeah, these look like sand dunes. Braided streams. And then you go back into more dune deposit. The Navajo sandstone, you're going to see a lot of pictures of the Navajo. It's really, really cool. And it's huge. And then you have shallow transgression. That means the ocean came back in on top of these desert sand dunes. And now the regressing sea, the ocean is receding, And then you get more of these windblown dune deposits in the Entrada. And you'll see some nice pictures of the Entrada. Okay, then the shallow marine, this desert deposit once again was overrun by the ocean, and tidal flat deposits, and then more sand dunes. And the salt wash member of the Morrison, great analog for the upper 50 meters of Prudhoe Bay. We'll see some pictures of that one, and that's meandering streams, small rivers, big streams. It's a lot of Prudhoe Bay looks like that. Shallow marine, and then Dakota beach deposits. You got transgressing sea. Now here's an interesting one: some coal, and coal is a very different environment than a sandstone or limestone. There's no mistaking it. Deltaic sands, barriers. This is right on the beach. And then you got the transgressing sea again. And, so you get the idea. There's lots and lots of depositional systems, and nobody is going to mistake a saltwater lagoon for a desert sand dune. Nobody's going to mistake that for a deep marine fossilized muck. So here's your complexity example in eastern Utah. You've got evaporite deposits. Those are basically when water evaporates and it leaves these desert salt flats behind. Limestone. And just think of the Caribbean, Fiji, Tahiti, offshore places in Hawaii where you're depositing coral reefs. Braided stream, that's the fluvial is the fancy geologic word, but it just means rivers and streams that are laying down sediments as they as time progresses. And then the fancy word, geologic word aeolian, that's basically windblown. So the Sahara Desert deposits, they're not put down by water, they're put down by wind. More examples of the complexity in eastern Utah. You got deltas, where the river runs into the ocean, and it spreads out, and it's as it enters the ocean, and then you form beach deposits where the water meets the land. Coal swamps. That's the only system that I know of that lays down coal is a swamp, freshwater swamp, with stagnant water. You got these deep marine shales, and they're not very pretty. They're badland stuff, but it's pretty diagnostic looking at this. You know how the sediments were laid down. Deep ocean deposits, a couple hundred to maybe a couple thousand feet deep. And then you've got multiple cycles again and again and again of each of these different deposition systems. Now this, we're going to talk, excuse me, we're going to talk at length about the San Rafael Swell. And here it is in kind of the south central part of Utah. And you got Moab over here, and what's the name of that town on the Nevada border? I'm having can't remember the town's name right now, but you got Interstate 70 coming through here. Well, St. George, that's the name of the town. No, it wasn't Georgetown, St. George. As you're driving from east to west, from west to east, so from California to Colorado, you guys would go across this, you would run across the San Rafael Swell. And what the swell is the sediments were all laid down flat, and then it's swollen. And I should do it like this. They're laid down flat, and then the center part of this swell, it's uplifted. And so you've got basically a kind of a round mountain, and then you're going to get stuff eroded kind of off the top of the mountain. So as you go west to east, you'll actually be able to see each of these different sedimentary layers exposed on the surface. It's a great place to study geology. This is a picture I took of the San Rafael swell back in February of 2016. And it's just gorgeous country if you like rocks. If you like forests, maybe it's not so great, but if you like rocks, this is really cool. And this is what the San Rafael swell looks like in cross section. So you're looking at it, the sediments were laid down like this, and then they're uplifted, and then they're eroded on top. So you can see this stuff here that was deep is now in the center of the swell. It's now on the surface, and that is the Moenkopi Formation. So this is the Moenkopi, and it's outcropping here, and it's buried. If you go either west or east, it's buried deep, but here it outcrops right on the surface. And if you want to see some other geologic system, you just get in your truck and drive a few miles, and you'll see all these different things that are laid down flat, but they're exposed on the surface. So that's one of the reasons why Utah is such a great place to do geology. So we're going to look at the now the pretty close to the San Rafael swell, like right in the middle of it, is Capitol Reef National Park. And so this is right here is what's called the Western Interior Seaway. I think during Cretaceous times, this was all, from Gulf of Mexico all the way to the Arctic. It was one ocean. And so we had a lot of marine deposits in this part of the United States. And if you look at the same thing as we had before, the environment, beaches and aeolian, tidal flat, marine, tidal flat, marine, coastal plains, fluvial, aeolian, Sabkha. And we don't have Sabkha in the United States, but if you've ever been to the Middle East, I spent a lot of time working in Qatar. And I also did a number of visits to the United Arab Emirates. And the Sabkha is this miserable desert crap that's right near the beach. So you got the salty, like the Persian Gulf, and then you got the land right next to it. The land is desert. It doesn't get much rain at all, but it gets a lot of salt spray from the ocean. And so you end up with this salty, yucky mess that hardly grows anything. It's nasty stuff. That's called Sabkha. Then you got marine, tidal flat, fluvial, beach, marine, deltaic, marine, coastal plain. You get the idea. We've got, again, a complex series of alternating depositional systems. And then one of the cool things, I really like Arches National Park. It's a great place. We spent lots of time in Arches, and we've already gone through this layering of the geologic events. So it's, again, alternating sequences of complex depositional environments. Just, there's no way a simple system did this. This is very complex. So we're now going to go and I'm going to show you a little bit of a wrinkle. It's pretty important for me. But what you're looking at here is this is near the bottom of the sedimentary column at Moab. And we're looking at the Honaker Trail sandstone. And the sandstone is this stuff here, this pinkish stuff. And in here, I should say this arrow is 6 feet tall. This is one of our guys that was on our field trip here. He's taken a picture of this exposure. And so that gives you some scale. So you've got maybe 4 feet of this, 3 or 4 feet of this clay-rich, fine-grained stuff. This is not sandstone. This is just sort of some low-energy, muddy stuff. But what's really fascinating about this, if you look at this, this rock is all broken up. You've got what's called en echelon faulting here. And an echelon is a fancy French word. It means stair steps. So you've got the sediments here are about 40 feet higher than they are down here. And so it's been down thrown like a series of stairs. So this sediment that was all laid flat is now stair-stepped down as you go from south to north. And I think the town of Moab is maybe 10 miles back that way. But what you have is this sandstone. This was hard rock. It was brittle. And when these stair steps went down, this rock just shattered, but it stayed intact. Each unit broke like a sheet of plate glass. You hit it with a hammer, but these sediments stayed flat-lying. So if you look at these sediments, they're all running essentially parallel to the surface, despite the fact that we've got these stair step faults and all this ruptured rock here. Now this 4 feet of this kind of grubby grayish brown stuff, that didn't break. If you remember the kind of toothpaste maybe that I had as a kid, I don't know if you did or not, where you had a green stripe and a red stripe in your toothpaste. And you could squirt that toothpaste around, and the stripes would stay, they wouldn't break, they would twist, and that's exactly what's happening here. This rock didn't rupture, it just sort of squirted like the toothpaste. So this is brittle deformation. This is ductile rock, and basically brittle stuff breaks and ductile stuff doesn't. So what a geologist would see from this is that, oh, okay, this rock was laid down, and then with this kind of shaly stuff in the middle, and then this became hard rock. This was still soft. And a long time after it was laid down, the faulting happened. But it didn't rupture this shale in here. It was still soft rock. So you can learn a lot about the deposition just by studying details like this. Here again is the example of the ductile versus the brittle. You can see this rock shattered, and this is like our green and red toothpaste. It just sort of squirted, but the rock is still intact. And this is important to guys like me. Now this a little farther north is what's called the Moab Fault, and the Moab Fault is really cool. There's 2,000 feet of throw on this fault, which basically means this part of the rock. This is my right hand, and so this part of the rock slid downhill 2,000 feet. So it's displaced by 2,000 feet from the left side to the right side, going down structure, displaced downward this way. And then the whole thing then has been, it may have been laid down like that, but it's all been eroded to where it's on the surface and we can look at it. And what you see is this Honaker Trail limestone. This is shallow marine. This is hard rock. You can see the bedding planes here. And then this Entrada sandstone in here is pretty weak. And it's just all busted up. And the stuff, again, you've got 300 million years ago, 180 million years ago. There's 120 million years of missing section over here. It's on this side, but it's been eroded away. Excuse me. It's been eroded away on this side. It exists. All the column exists on the right side. And this is our field trip. These are the guys on it. I'm out of sight here somewhere. This guy here was a friend of mine, and he is a structural geologist. And basically what these guys do is study what happens to the sediments after they're laid down. So he's explaining to us all the detail about the Moab Fault. And it just looks like God took a knife. It is so sharp. And so this side fell down, is that 2,000 feet, 100 plus million years of stuff now is over here that doesn't exist over here because it's been eroded away. So what we have here is the brittle deformation. The sands that were laid down became sandstones. They were busted up by faulting. They were then subsequently eroded away. Thousands and thousands of feet of stuff were eroded away. And there's huge amounts of geologic time that are just flat out missing on the left-hand side. So this is a cartoon cross-section of the Moab anticline with the Moab Fault. And these sediments again were all laid down flat lying. And what happened here is this folding happened, and then this part fell down. And here's our displacement of 2,000 feet right here. So you've got very different rocks that are on the surface exposed next to one another. So what does it mean for the Moab Anticline? 10,000 feet of flat-lying sediment was deposited. This took a period of about 200 million years. The Honaker Trail Formation was compacted and cemented. It was cemented enough such that when the faults happened, the sandstones were brittle and they shattered. It was massive faulting, over 2,000 feet, which is just huge. That's not very common. Then the entire region was tilted, and you've got the San Rafael swell. You've got this erosion happening so that we can drive on the surface and see all the different outcrops. Thousands and thousands of feet of this 10,000 feet have been eroded in spots. And this cementation, faulting, tilting, and erosion happened a long time after these sediments were deposited. So this didn't all happen in the same 1 year. It cannot be explained by a simple flood event. So now we're going to go to my favorite deposits. This is the Entrada Formation. If you ever looked at a Utah license plate, this is Delicate Arch, and this is what's on the Utah license plate. Really cool place. And so we're on top of the Entrada Formation, looking at Delicate Arch. We went a couple mile away, whatever, and we're now down in the Navajo sandstone, which is this huge, thick Aeolian desert deposit. And there's our buddy, the Delicate Arch, right up there. So this thing is, there's a guy here. I don't think he's one of our guys, but still 6 feet tall. So this whole thing is like 60, 70 feet tall. And so there it is, that's 60 to 70 feet. And you just have to estimate how many hundreds of feet thick this is. So you got hundreds of feet of sand. And then this is just another cool picture of Delicate Arch. It's just this is a great place. And this was our party. We had 23 geoscientists and engineers on this field trip. And even science people, geo nerds have to eat. So I'm digging into my backpack. This is me here in the blue shirt. But I love these trips. They were just great. And you learned a lot of stuff. And from Delicate Arch, this is what the Navajo sandstone looks like. So we were down here taking pictures back of Delicate Arch. Well, this is what the Navajo sandstone looks like. And you see all these rounded things. You don't have to have much of an imagination to say, okay, these are fossilized sand dunes. And they look like they are because that's what they are. Now we're going to take a look at the Navajo sandstone. And we're now in Zion National Park, kind of over by the very eastern border of Utah. And so I guess we're down around Nevada and Arizona. And but this is all still within Utah. And these things are hundreds and hundreds and hundreds of feet thick. And we had just hiked to a place called Angel's Landing. If you guys ever get the chance to go to Zion, bucket list, hike Angel's Landing. If it doesn't scare the snot out of you, then you're a much braver man than I am. You hang onto a logging chain and it's 1,000, 1,500 foot straight drop. It's like my new best friend is a chain. But we're coming down, and this is a picture of my wonderful wife Sylvia here for scale. There's a couple of people down here as well, maybe even better for scale. And you can look at the bedding planes and see how these things are almost flat lying. These guys are tilted maybe 40, 45 degrees. These guys over here are kind of scoopy. This stuff here, if you look close, you can see these bedding planes. They're going all over the place. There's some this way, some flat, some that way, 3 dimensions, you know, some going this way and some going, they're all over the place. It's not a single, like, Noah's flood depositional. These are sand grains that have been deposited by wind, and they're going every which way. And this Navajo sandstone in the early Jurassic, so it's the middle of the dinosaurs, is the result of the largest known sand desert in the history of planet Earth, which covered an area like today's Colorado Plateau and beyond. It goes, you know, New Mexico, Arizona, Colorado, Utah, Wyoming, Montana. I think it might even go into Alberta. This thing's sand dunes, it's huge, bigger than the Sahara Desert. And so there's only one kind of depositional system that can lay rocks down like this. Only one. And that is this. This is, you know, today's Sahara Desert. If you've seen the movie Dune 2 recently, just think of the planet Arrakis, where the spice comes from. That is what Utah and Colorado looked like during this time frame. It was just giant dune fields, and some are going this way, some are going that way, and depends on exactly where they are. You'll get sedimentary deposits that have different angles, and it's all the same desert, but different dunes. And this has absolutely nothing to do with ocean water. This is desert, deep desert. So the Aeolian deposits, in addition to being a great place to play tourists, you know, this is great for geologists. You got these huge Aeolian dunes, like the Sahara Desert. It's wind blown, and it's angular. It's got sharp edges. You know, when you have flowing water like a river system, this stuff it collides with other rocks, and it basically everything gets kind of rounded. But these things have sharp edges, and they hit one another, and that results in these frosted sand grains. They're not rounded grains, they're frosted. They've impacted other sand grains. Very thick deposits, up to 2,200 feet of sand at Zion National Park. And it was deposited just all over the Western US, except you guys in California didn't get any of this. So you got lots of other stuff. So these Aeolian deposits, there are no aquatic fossils found in this. Nothing to do with water. They are separated by fluvial deposits, which basically means on occasions you had a lot more rain and rivers ran across this stuff, and then it changed again, and more deposits. You had marine shales, which basically meant the ocean came in and deposited this fine-grained yuck. And basically Noah's flood could not possibly, there is no way that any of this sedimentation could have been done by Noah's flood. This is deep desert. So now we're going to go up structure quite a bit. It's Jurassic. Okay, I was going to say, what's the age of this sediment? One of the things that when you've been around for a while in geology, you'll notice that the fluvial intervals, the distributary channels, and all the meandering streams, when you look at them in like a road cut or something, or like what we're looking at here in the canyon, it looks like a stack of playing cards on the side. It just looks like you're looking at the edge of a deck of cards. You got little fine layers, just like a deck of cards. And that is exactly what we're seeing here. Is these are the meandering streams. This is a big distributary channel. So this is a big river system, and this is right in the middle of it. And got one of our archaeogeologists, her name is Bev, and she's talking. Actually, I'm the guy in the blue shirt again with my Indiana Jones hat. And but these are not ocean sediments. These are These are onshore meandering rivers. Good example of Prudhoe Bay Zone 4. This is the kind of stuff that was 9,000 feet deep, Prudhoe Bay. I couldn't see it, but I can look at this and get an idea of what's happening in Prudhoe. That's why we did these trips. There's another kind of depositional system, and here's this western seaway again. And of course, it moves back and forth somewhat. But in this part of eastern Utah and western Colorado, you get this formation called the Book Cliffs. And underneath it, you have this really nasty formation. It's an ocean bottom formation called the Mancos Shale. And it's just deep sea muck. There's a geologist who come up with a better word than muck. That's my word. And this is what the Mancos Shale looks like. It's this just ugly stuff. It has no real form. You get a hard rock like this stuff up here, you can form cliffs, but you get into this like soft, crummy Mancos Shale, and you see how the angle changes. The angle of repose changes because this stuff does not withstand erosion unless it's protected by something much harder above it. And so this is a picture out of the geo textbooks and of the Mancos Shale. This is a picture I took. I think that was back in 2016 in the wintertime when we were rolling through here. And you can just see that this, it's just uck, and it hardly grows anything, nothing but a few weeds. It's just badlands, and that's actually the stuff that you see in badlands deposits. So the Mancos is easy to spot. If it's just horribly ugly, it's probably the Mancos. Okay, we keep going, and we're now looking at deltaic sands. This is where the rivers flow through flow into the ocean, and it just before it goes into the beach, into the ocean, it spreads out. You get the delta fan, and then you get beach deposits. And anyhow, these are two what are called sedimentary geologists, both Bev and Bo. A friend of mine, his real name is Beauregard. His last name is Ty, so his nickname is Bo Ty. So I think it's kind of cute. But excellent postdoc, smart people, much smarter than me in terms of the geology. And they're explaining to us the whole delta front system. So let's look at the depositional environments in southeast Utah. We'll start at the bottom like a good geologist would, because that's where the rocks first laid down. We looked at the Honaker Trail Formation, and that was limestone, rivers, streams, so shallow marine rivers and streams. We looked at that in detail. And by the way, before I go on, this black bar right here, that's 100 meters. That's a 30-story building. So that gives you some idea of how thick these formations are. And then we come up here to the Navajo sandstone. These are the deep desert dunes again. And then the Entrada Formation, it's this great place. They've even got a diagram here of delicate arch. So that's the member that forms the arches, really a lot of them. And then you get into the Morrison Formation, the analog for the upper part of Prudhoe Bay. It's rivers and streams. And then you get this Mancos Shale. That's just the deep marine muck, hundreds to thousands of feet of water depth. And then up to Tusher Canyon, and we've got rivers and streams at the delta front. So this is again where river runs into the ocean. So you've got complex layering here. So question number one, could the entire geologic record have been laid down quickly thousands of years ago in a global flood? And the answer is not in Utah. There are many depositional environments. Some, like the flood, cannot produce at all. And there's no way, there's just no way that a deep desert deposit can be characterized by Noah's flood. It exceeds my ability to imagine a way you could do that. Some are very slow. And for example, forming limestone reefs, this is a slow process. These are critters that, you know, they might grow this much in a year. That there's no way that hundreds of feet of limestone are formed with all kinds of fossils and stuff in it. Coal seams, trees grow, fall in a swamp, they rot, they don't rot, excuse me, the lack of oxygen, they don't rot, fall in, and you build up a coal seam, however many feet that is thick. That takes a lot of years. It doesn't happen in one. And you got many complex alternating sequences, everything from beach deposits to evaporites to coal swamps to delta fronts to deserts. You got all kinds of these complex alternating sequences happening again and again and again. And then you've got this, after it's deposited, you've got a lot of stuff going on. You've got this faulting, you've got tilting, stuff getting eroded, so we can actually see it. And these things happened a long time. Let me get the right slide here. I think I went the wrong guy. Boy, I really did. So basically, there's no way Noah's flood explains Utah. And any place you look at on planet Earth, you're going to see essentially the same story, difference in the specifics, but the issue of complexity simply can't be addressed by Noah's flood. So now we're done with the geologic deposits. Now we're going to take a look at the biodeposits. And maybe somebody out there can guess. This is from my home state of Alaska. Probably doesn't take a rocket scientist to look at this picture and figure that out. Anyhow, this is a drilling rig on the north slope of Alaska. It's an exploration rig. There's nothing around it. And I spent a lot of time on rigs like this. And we build ice roads. The road is maybe made out of 5 feet thick ice. And you bring heavy trucks and the drilling rig and stuff across it. You do your business here, drill your well, find out what you got, move everything off, and then next summer it melts and there's no trace you were ever there. So it's pretty good technology. And if you found something, well, now, okay, we'll, instead of ice, next time we'll build that road out of gravel and we can get to it. But this is what the exploration wells look like on the north slope of Alaska. Okay, where's my, there it is. Okay, and this is, gosh, this has got to be 20 years ago now. So what is a biodeposit? I'm going to show you some of those, but first of all, I'll tell you, I do have something in common with Jesus. We've both walked on the sea. Now, the difference is this is the Arctic Ocean and it's frozen solid. And even though this is June, and this is, okay, June 2005, even though it's frozen solid, it's June and this ice is starting to develop some leads. So you really don't want to trust it too much. But I'm out here with a professor from the University of Wyoming, and I'm giving him a tour of our water injection facilities on the North Slope. Back here, you can see off in the distance, is another field I worked on called the North Star Field. It's 10 miles offshore in 40 feet of water. So it's an offshore field, but it's pretty shallow. And so 10 miles of very gentle increasing depth as you go from Prudhoe Bay to North Star.
Pat, could I make a comment?
Yes.
Hi, it's Randy. My apologies, but we actually have to leave the room here in about 10 minutes.
All right.
So if you don't mind kind of going to your final conclusions, I would appreciate it. Thanks. Okay,
I'll give you one thing real quick. And that's just the reason why you get the same story at Prudhoe that you did, or at Alaska that you did in Utah. Prudhoe Bay, 12,000 foot fluid column or sand column was deposited. Top 2,000 feet was frozen from 2.5 to 12,000 years ago. The permafrost has been thinning for the last 12,000 years, but this was frozen before, during, and after Noah's flood. So there are no possible contributions to the sediments on the North Slope of Alaska from Noah's flood. There's a whole bunch of bio stuff that we don't have time for, but the bottom line question, could all the biodeposits have been formed thousands of years ago in a global flood? And the answer is not in northern Alaska. A lot of depositional environments, just like in Utah. Some are very slow. Again, we had 1,500-foot thick column of limestone that was formed on the North Slope. It's called the Lisbon limestone. A bunch of coal seams, both down deep and up shallow. So again, long time in fresh water to form coal. Just like we saw in Utah, lots of different environments going on. There we go. And so there was an idea of, I got to ask, okay, what could have happened? And here's the scenario that's listed out in Genesis 8. The tops of the mountains became visible. But if you look at verse 9, the dove found no place for the sole of her foot, so she returned to him in the ark, for the water was on the surface of all the earth. Well, clearly, you can see the mountains in the distance, but from the dove's point of view, there was nothing but water. So the use of water on the surface of all the earth does not mean global. It definitely means something very different than global. And here's a possible scenario for Noah's flood. The Mesopotamian floodplain, that was where all the place names were. And the fountains of the Great Deep, that could be storm surges or tidal waves caused by earthquakes. And the waters invaded deeply, aided by massive rainfall. And then the water recedes. Basically, the flood could have happened in what's today's Persian Gulf. And the Mesopotamian floodplain looks like a giant bathtub. There's the Persian Gulf. But during the ice ages, which was on when Noah's flood almost certainly happened, the Persian Gulf was dry. It was. I worked for 5 years in this Al Shaheen field. This is Iran. This is Saudi Arabia here, United Arab Emirates, and this is Qatar. And I worked this Al Shaheen field for 5 years. And it very possibly is the location of the Garden of Eden. It's today on 200 feet of water, but it would have been 200 feet above sea level prior to 15,000 years ago. So Eden is where these 4 rivers come together. We know where the Tigris and Euphrates are. Pison, Gihon, nobody really knows. But this area here was the dry land during Noah's time. And that's about out maybe in here somewhere. This is the Straits of Hormuz. And so a possibility is that that Persian Gulf is where where the Garden of Eden was. So the overall conclusions, Genesis flood is a very simple event. 1 transgression, 1 regression. Seas went up, sea went down. The geologic records and the biodeposit records are very complex, and the flood cannot explain either one. Again, depositional complexity, structural complexity, chemical and thermal complexity, the cooking of sediments that contain organic material into oil, the thermal complexity like of forming thousands of feet of permafrost can't happen in a year. Flood can't produce deep desert sandstones, can't produce limestones, can't produce thick permafrost. So overall conclusions, the flood, my conclusion, and I think this is Reasons to Believe's conclusion as well, is the flood was restricted to the Mesopotamian floodplain. Everything up through Genesis 11, all the place names are in Mesopotamia. And local flood in the Mesopotamian floodplain would leave very little remaining evidence, especially since where people were living is now underwater, under hundreds of feet of water. So that's my final slide. And any questions or anything we have time for, I'd be happy to hit.
Thank you so much, Pat. That was really informative and a lot of evidence for your position. So I really appreciate that. Does anyone have a quick question here? I'll just say, if you want some further information, this book that I'm holding up, Navigating Genesis by Hugh Ross, gives some other detailed information and some supplementary things to what Pat presented to us this evening. So I would recommend that for further reading. And Jim, did you have a?
I have one question for Pat. You sent us a PDF and a PowerPoint. Is that okay to share with the rest of the group?
That's why I sent it is, yes, please share. A lot of these graphs are too small to read, unless you're looking at it in the computer kind of format. So that's why it's there, is to share.
If anybody wants that, please email the email address that you would have received the invitation from, and I can send it out.
Thank you for your presentation. That was incredible. Two quick questions. Do you, well, the one I can think of right now is, do you have like a best 2 or 3 books that you think are really good on things of science and old earth creation? I know there's a lot of RTB stuff, but say something that's not on the RTB thing that you find is really good. Oh, and the other thing is, do we have permission to perhaps ingest this and use the slides at perhaps a presentation at our churches? Yes,
That's why I did this, and I've given this to a number of chapters around RTB, and maybe somebody will profit from learning this data and realizing that scientifically there's no way to defend the young earth creation position. If you're going to do science, you're going to have to do science. Doctrinally, I think one can make a case for this or that interpretation, but remember, truth has to mesh with truth. And if the young earth position just doesn't mesh with science, then one or the other of these interpretations is wrong. And science on this subject is so solid, it's so powerful, that I think it's the interpretation of theology that needs to be adjusted. There's no way this science is gonna go young earth. It's just not.
In your quick and dirty reading list?
And what I'm gonna do, have Jim send me an email, Jim or Randy send me an email, and I will look up some of the reference materials. I'd rather not give that tonight. I'll give it to them in an email of what I found helpful. And is that okay? We can give you a reading list by email to your chapter, and then Randy and Jim can forward that to people.
My turn? Okay. Well, back when I was trying to be a young earther, I read a lot of books on how the mountains got formed. Well, the earth was pretty level before the flood, according to their model. And that's how the water could cover all the mountains, because the mountains weren't there and the flood made it. And that's why the ark was 1/6 units, and it could tip and roll 90 degrees and stay afloat. And the great power of this water actually formed all the mountains. And if that's the case, basically all geological structures on the earth would have had to have gone away. But earlier in Genesis, we have a description of where the Garden of Eden was. It was it describes 4 rivers that the Garden of Eden came out of. But oftentimes, maybe it's me or maybe it's someone else, people look at where the mouths of those 4 rivers must have been and say, well, that must be where the Garden of Eden was. But that's not how, in my mind, the Bible describes it. I could be wrong. It doesn't say that the Garden of Eden was this, 100 square miles at the mouth of the rivers. It said it was at the headwaters, which means this Garden of Eden is 1,500 miles across, or 1,000 anyway. So, but maybe I'm wrong. Something to think about.
It's the, appreciate your sharing on that. And it's having the humility to realize we don't know where the Gihon and the Pison really are. This is some of the better theories about where they are, but I'm very humble in terms of what I know about Garden of Eden. It's in there somewhere. It's within a handful of hundreds of miles from where these rivers potentially all came together. So it's in this general area somewhere. That would be my best answer.
But my point is, the Bible doesn't say it's at the headwaters. It doesn't say it's at the mouth. It says it's at the headwaters, which is in the mountains, which is, most of Turkey is where the Garden of Eden was, if that's the case, unless I could be very wrong.
It's hard for me to come up with a conclusive doctrinal position on these four rivers and what it all means. Adam and Eve were in the garden, and it was one single physical place, and it's in this general part of the world. I think I can say that.
Well, again, thank you, Pat, for a great presentation and your time. I know you're in Colorado Springs, so it's even later there. So we really appreciate your time and effort, and we will be in touch, but and look forward to your information that we'll pass on. So again, thank you so much for being here.
Well, you're very, very welcome. So I wish you and your chapter well. I don't know when the chapters go away, but
thank you. Thank you. So
Yes.
we'll say goodnight. Just by way of explanation, next month we will have Balajit Nangram, who is from India, come speak to us, obviously from Zoom. He's not coming here. And it will be on engaging your Hindu neighbors. So I think a lot of us have neighbors and friends and colleagues who are Hindu, and sometimes it's hard to know how to approach them and how to share the gospel with them. So we're looking forward to that next month. We will, as we mentioned last month, we are in a transition time because the RTB chapters are being retired as of the end of June. And so we will be announcing a new name for our group. But that is pending still, but that is something to look forward to. And so with that, let me pray, and then we will be dismissed. Father, again, we thank you that we could be here this evening. Thank you for Pat and his presentation, and the truth that your word and your creation do mesh together, and that because of that, we can be confident that we can share the good news of our Lord Jesus Christ with everyone, including those in the scientific community. And we ask that you would give us your grace and your purpose moving forward, that we might be good ambassadors for you. We thank you in Christ's name. Amen. All right. Well, that concludes our evening. And again, thank you all for coming here, and those of you on Zoom. So we look forward to seeing you next month.